answer the question about what's happening on the screen. Okay, so thank you everyone for coming back. All right, so the first talk, if you remember, was titled G-manifolds and equivariant stable homotopy theory, and then I titled the second talk G-manifolds and equivariant Equivariant K-theory. Okay, so as a quick reminder, so last time I stated a few manifold classification questions and showed how, if you state them in the equivariant context, they motivated a lot of equivariant stable homotopy theory, even starting from the very first, things like Poincare duality. And we ended talking about a bunch of the scissors congruence questions that are also a kind of manifold classification questions. And I did talk quite a bit about K-theory last time. It was not classical K-theory. Everything I talked about at the end of last time was squares K-theory, so this new form of combinatorial K-theory that gives you K-theory spectra for scissors that encode scissors congruence relations for manifolds. But I want to point out that last time I did actually not ever talk about equivariant K-theory. So all the K-theory that you saw was just non-equivariant K-theory spectra, so squares K-theory spectra. So it was for equivariant manifolds, right? So we showed that that you can generalize the scissors congruence of manifolds K-theory squares K-theory story also to categorify equivariant SK groups, right? But that was still a non-equivariant spectrum. But then we had some results, right, that this equivariant SK form a Mackey functor. So there's some shadows that indicate that those should be fixed points of genuine equivariant spectra. But yeah, I just wanted to point out that I have actually never talked about a genuine G-equivariant K-theory spectrum in the last talk. Okay, so in this talk, and then I told you that we were going to focus on question 3 from last time today, which is about understanding if you want to not just classify manifolds, but also their diffeomorphisms. That's connected to this H-cobordism space, and this is what we're going to talk about more today. So maybe let me just recall. So from last time, let me maybe just recall the big theorem, the classical H-cobordism, S-cobordism theorem. So by Smale, Varden, Maser, and Stallings. So S-cobordism, H-cobordism. So that if the dimension of the manifold is at least 5, and we're in the smooth case, so M is a compact smooth manifold. Isoclasses of H-cobordisms on M were in one-to-one correspondence with elements of the Whitehead group, which by definition is a quotient of K1 of the group ring of pi1M by plus minus the elements in pi1. So this is the first instance where K-theory comes up. So maybe actually on the side, let me put some references for some of the background stories here. Some that I mentioned last time. So for the non-equivariant higher version story, I will highly recommend John Rognus's notes, lecture notes from 2006. So it's called Lecture Notes on the Stable Parametrized H-cobordism Theorem. Okay, so these are very wonderful notes that are very inspiring about the whole story. And for the equivariant, so this is, so John's notes, right, are on the higher version story, non-equivariant, and for the equivariant pi-naught version, which was known, as I said last time, kind of everything you can find in Luke's book, transformation groups and algebraic K-theory. So this was Wolfgang's Habilitationsschrift, and he collected all the results, including his and many people's. So this kind of contains everything that was known at the time about the equivariant pi naught version. So on the group level, all the results that I mentioned last time. Okay, so now, we want to go higher. So we actually have a whole space of H-cobordisms on M. So this is going to be up to the diffeomorphism that fixes so up to that fix M, so the bottom, and M maybe has boundary, and then also would want to fix the boundary of M times I, and maybe a neighborhood, and a neighborhood of the bottom and sides. And the Q simplices in this space are going to be H-cobordis bundles over delta Q. So it's the space that parameterizes H-cobordis bundles. And as what we saw in this theorem, right, so from this theorem, we see that its pi naught is computed. So this is the pi naught by definition. And the pi naught is computed by K-theory. Okay, so now we can ask, we can ask the question, what about all the higher homotopy groups? So are all higher homotopy groups also computed by K-theory? So this was the big question, and the answer turns out to be yes, but only in a range. And so for this, I need to introduce now the stable version of the H-cobordis space. So there exists a stabilization map. So HM going into HM times I. So roughly you want to, you want to cross a manifold with I, and then, you want to cross an H-cobordis with I, but of course this is a little problematic, and it raises some subtleties in the smooth case. So there's also stories in the PL case and in the topological case, right? Because when you get corners, first of all, we see you get manifolds with corners, and then also, so it's not going to be trivial on the side anymore. So there's ways to handle this. So let me just show you one nice, elegant way to make the stabilization map and make everything functorial. So instead of talking about H-cobordisms in talks, because it's much nicer to explain, let me do an interlude and instead talk about pseudoisotopies. So the space of pseudoisotopies differs from the H-cobordis space just by a looping. And the same ideas will apply, but it's a little bit easier to explain what to do if you think about pseudoisotopies. Okay, so let me remind you. So a pseudoisotopy is going to be, so it's a diffeomorphism from M times I to itself, which is identity on m times 0 union the boundary of m times I. Okay, so now suppose that we want to define a stabilization map from, so again we have a space of pseudoisotopies, and suppose that we want to go from this to p m times I. Okay, so given a diffeomorphism of this form, F, we want to produce a diffeomorphism of m times I to m times I times I. Okay, so what is the first idea that you might have? Right, so this is I times I, the square, so think about this whole thing being right times m, and what we could do is we could make a picture like this, and on each one of these lines we could put our f, and just make this identity outside of this. Okay, so this is a good idea, and you can do this, and it will give you this map, but or not quite, because the problem is smoothness at this cone point. Right, so the problem is well, we need to put an extra condition in order to ensure smoothness there. So we need to put a condition to ensure smoothness at the cone point. And this is not very hard. You could ask for f to be a product near the top. But then the problem will be that once you stabilize, so once you do this, this will lose such a condition. Okay, so that's not very good. So, but we can try a little harder, and the idea that Kiyoshi had way back, which is very nice, is to instead work with what's called a U-shape. Okay, so it's a U-shape because it looks like that, and just put our diffeomorphism, our f's on these lines, and then here you have whatever the constant diffeomorphism that you had at the top, and identity outside of here. And now this is very nice. You can, there's no condition to lose, and you can compose such maps and keep going. So this is what Kiyoshi used in his proof, and I'll mention his theorem in a second. So he proved so the stabilization, a stabilization result. So exactly the connectivity of the stabilization map. And in order to make it precise, this is what he used, U-shapes. Okay, but an even better idea that we used in our recent work, and this is also a brilliant idea of Kiyoshi, kind of pulled out of a magic hat. It at first looks crazy, and then it's like, there's no way this is going to work, but then it turns out it's like magic. So the idea is as follows. So for a pseudoisotopy, you can consider the double. So consider its double, F bar. So to save some time, maybe let me not write the definition, because it will be pretty obvious, right, what it is. I'll say it in words. So we're doubling the interval, and you're really just doubling, so you're making the unique map that's going to be commute to the reflection across the interval. Okay, so now we're going to say that F is mirror if the double is smooth. Okay, and we could just work, so you can show that you can just switch to working with mirror pseudoisotopies. So these spaces are actually homotopy equivalent. Okay, so instead we're going to work with the mirror ones, so these doubled ones. And it turns out, crazily, that if you do the first idea, right, so if you just, so if you define a stabilization, so again, maybe the picture V is going to be I, just R, a line, so, but we can do this even equivariantly, which we'll be interested in later. So we can define, we can use this first idea, and now our things are mirrors, so everything is double. And you can just do this and put your F bar on these lines. And there may be unexpected identity outside. And the unexpected thing is, okay, so first is, this is actually smooth. And it's also mirror. And so the thing that didn't work before, if you just double it, just works. And this is, maybe I will let you, if you're curious, you can go and look in our paper, but it's just a little trick from calculus about even and odd functions. So the components of such a doubled H-cobordism, so one function is even and one is odd, and this is with respect to the second variable. And now you can play a little game and write the coordinates very concretely, and this actually now turns out to be smooth. And the other magic thing, which again you can just write down the formulas and verify, is that if you do this twice for two different in stages as opposed to doing it all at once, this is actually equal. It's equality, not even just isomorphic. So that's just kind of magic. Okay, so this is the idea. And the idea is you can also use this for H-cobordisms. So we can also do this doubling trick for H-cobordisms. And also, so it turns out, so for pseudo-isotopies, everything is really pretty and very easy to check with formulas. For H-cobordisms, so this is why I didn't want to state it for H-cobordisms, smoothness is a bit of work. So to check smoothness at that middle cone point, like you actually have to work a little bit with charts and such. And then also, we don't get this quite as magic that you get equality here, but you can still build an isomorphism between these two. And this is one of the main ingredients that goes into making this H-cobordism functor into an infinity one functor. So you have to build, your vibration, and you need to build a bunch of coherence there, and this is one of the main ingredients. Okay, so, and let me maybe put here also what we think is a good idea is to just work with corners. So just let the corners be. But, okay, yeah, so M might be a manifold with corners, and it will be, right, once you cross with intervals. But then your H-cobordism is only going to have corners along the boundary of M times I. Okay, so this was a little bit about this stable, oh, I should not forget to mention, right, the big theorem of Figusa from the 80s is that if you look at the stabilization, sorry, I also should have defined this, I guess I didn't. So this is now the co-limit of H M times I to the N. So the theorem is that this is roughly N over 3 connected. So there's a precise number that it has that's roughly that. Okay, and now so why do we care about this, right? So recall I talked about this a little bit last time. So this stable H-cobordism space, right, was...
The N's are different now, and the activity is the manifold dimension.
Yes.
Whereas the co-limit is...
Yes, thank you. Great point. So let's make this a K. And yes, n is the dimension of n. Okay, so why do we care about this? So recall I mentioned this a little bit. There were some fiber sequences that came up, like if you want to compute B diff m, and this was a main ingredient for computing the homotopy of B diff m. And this is a main reason to care about it. Okay, so now the big theorem, right, first suggested by Waldhausen and proved with Yaren and Rogness. Right, so this is celebrated manuscript of Waldhausen, Yaren, Rogness. So the theorem, and this was the inspiration for defining A theory, algebraic K-theory of X. And the theorem is that this breaks off as the suspension spectrum, so the stable homotopy of X times something called the Whitehead spectrum, and with a property that if I plug in a compact smooth manifold, this is the stable H-cobordism space. So A theory is defined for all spaces. And the analogy with the theorem above, right, so the theorem above told us, so maybe actually, let me just write it here, maybe even in a different color, right, so this told us that pi naught of the stable H-cobordism space was a K theory, a K group. Okay, K. So it's computed at least in terms of a K group, and then this tells us that the entire space, even at the higher levels, can be computed in terms of the K theory space.
So is Whitehead for X a space or a spectrum?
Here,
Yes.
X is a space.
But Whitehead of X.
Oh, Whitehead of X is a spectrum.
But then down here it's a
Yes.
space.
Wait, here, this is, yes, I guess I am conflating spaces. So let's say okay, I guess I didn't write a notation for infinite loop spaces. Yes, thank you, John. So I'm conflating spaces and spectra. So maybe I should have, so actually, yes, let's make this Q. Yeah, so we have this decomposition of infinite loop spaces. Okay, so now the goal is to do this, and maybe we can call this a conjecture. Right, to do this in the equivariant case, if M is right, a smooth G-manifold, compact, and so if we want to understand the equivariant version, okay, so I'm also going to make one assumption. Oh, actually also, let's make another standing assumption. G is going to be finite in this talk. So the other assumption that I want to make about corners, so we said we're going to allow manifolds with corners, but in the equivariant case, we're only going to allow for what I will call trivial corners, or trivial G corners. And what this means is, so locally it will be modeled by G times over H, some representation. Okay, so this makes it a G manifold, but now the corner part is just going to be a trivial. So this has trivial G action. Okay, so this just is a technical hypothesis that makes many things work much nicer. I think many things that we have proved technically would get more complicated, and there's no point because this is all we need, right? So we really care about a manifold maybe right without corners, and we just care about being able to cross the manifold, taking products of manifolds with boundary, like dV. And when you do that, you only get things of this form, right? So something with not trivial corners would be if you flip across a diagonal in a square or something, but that's not going to show up if we just take products of manifolds, of G manifolds with boundary. Okay, so right, so maybe the conjecture, right, would be something like, okay, so now these are all G manifolds, right, where this is a G spectrum that should have, so now I'll take its infinite loop space looped once with the fixed points, really, that this should be some equivariant H-cobordism space stabilized. Okay, so let me make sure, right, that it's clear that this is, the whole statement is a conjecture, and we don't know how to show all of it yet, and actually I'm not even sure anymore if it's necessarily true that you have such a splitting. So I will tell you what we know how to show. Oh, sorry, this was when M is a manifold. Okay, so I told you a lot of the pi naught story. So maybe let me also just say, so before we started working on this, which was now, I guess, many years ago, right, so this was not defined. And of course, this is something, right, or this, right, is something that, that also we want to define in the equivariant case. Right, so these are all things that I need to introduce right now. So let me remind you a little bit. So what I said last time was maybe this. So we had a version of this theorem by Araki and Kawakubo, that said that, you know, such a theorem didn't hold on the nose equivariantly, but you had to cross with a representation to make it true. So you can already guess, right, what we'll want to do to define a stable version of the H-cobordism spaces. We'll want to take a co-limit over crossing with representations. Okay, but before even stabilizing anything, okay, so let me mention one other theorem from way back that you can find in this book of Luc that I didn't mention last time. It will be generalizing. So last time I did talk a little bit about isovariant H-cobordisms and isovariants, and I said it's a good thing to learn on day one of an equivariant workshop because it might come up again, and then you saw it already came up in Mike's talk. You might have noticed he didn't call it isovariant, but isovariant maps came up in his talk. Okay, so Browder, Quinn, and Rothenberg showed that if M is a G manifold and the dimension, so remember this was the H stratum, so points of isotropy exactly H, and WH acted on this freely. So if these have dimension at least 5, then if we look at isovariant H-cobordisms mod diffeomorphism, so what would be the pi naught of an isovariant H-cobordism space? So this is the Whitehead diff, the equivariant Whitehead group, and this splits over conjugacy classes into Whitehead groups of these guys. Okay, so this is a theorem that, so here there's nothing stabilized. You don't need to cross with any representation. So again, it's a statement that holds for isovariant H-cobordisms. So now let us define, so we can define an equivariant H-cobordism space. So whatever I said before works equivariantly. You can make it into an infinity one functor into the same way. And so now we're just looking at equivariant H-cobordism. So of course, I'm sweeping a lot of details under the rug, like you usually want to put a bunch of extra properties and conditions on your H-cobordism to interact with them. So I'm keeping it simple here. And we can define a stabilized version by taking the co-limit over representations of these guys where we cross with representation disks. Okay, so now what we can show, so with Udvuli, Igusa, and Kerry Malkiewicz is, and maybe I should say this is in progress since it's still not completely written and out, so it's good to be careful. So if we assume, so if we make the same assumption here, so we can generalize this theorem now to the space level. So we can also define an isovariant. Sorry, I only defined the equivariant H-cobordism space. You can also define the isovariant one, where you only take the isovariant ones. And it turns out that you can show this splits, right? So we have such a splitting on the space level. Okay, so far we have not stabilized anything, but now the stable result, right? So from here we can deduce a stable result, and maybe let me remind you how the Araki-Kawakubo theorem that I presented last time went, right? So they had a theorem like this, but it said that equivariant isoclasses of H-cobordism on M, or so it said that an H-cobordism is trivial, an equivariant H-cobordism is trivial. Sorry, the Whitehead torsion is 0 if and only if the H-cobordism is crossed with a representation was trivial. And as I explained last time, the way they show this, right, is reducing it to an isovariant statement that holds on the nose, and then using this result that if you have enough gap hypotheses that become true when you cross with representations, isovariant and equivariant become the same. So in a similar spirit, we can go from this to a stable result that ends up being, so this is now our stable H-cobordism space, stabilized with respect to representations. And here we get, MHWH. Okay, so further you can identify these terms like this. Okay, so this now looks, so this should look, suspiciously close to a well-known beloved fact in equivariant stable homotopy theory, right? So if you ever wanted to get something like this, so actually let me maybe, make a remark right here, right? What's that?
Could you lift the board?
Yes. Is this good?
Sorry, Mona, in the formula on the right-hand side here, so the stratum on WH are non-compact manifolds?
Actually, we compactify them. So maybe I should put, but those are homotopy equivalent spaces. But yes, we compactify them.
But then H-cobordism on such a thing, there's no particular control over the, well, I guess if you compactify them,
Right.
it's control.
Yes. So you remove like an open neighborhood of the fixed points you want to remove. What did I want to say? Yes. So let me recall this right beloved fact here that so we have a Tom Deke splitting of fixed points for the suspension spectrum, right? So these are suspension spectra of fixed points, homotopy orbits with respect to the Weyl groups. Right? So it looks just like this, and this was kind of, it looks just like this, and this was our goal. Okay, and before moving on to K-theory, let me say one thing there. Oh, sorry, this is not one I want to remove. Okay, I'll leave it like that. But the one thing I want to say is that to prove this splitting, right, the first one from which we deduce the second one, so that really, you really have to use isovariant things. So maybe think as an exercise, even in the case where you have CP and two kinds of fixed points and you were trying to write a fiber sequence, so something like going from an H-cobordism over the free part and extending by trivial H-cobordism to the whole thing, and then another map that restricts an H-cobordism to fixed points. That's not going to be a fiber sequence if you work with equivariant H-cobordisms. So you really need a strata to be preserved under all the homotopies in order to be able to obtain the splitting. So this is why it's important there, and we need to first prove an isovariant result. Okay, so now the big question, right? So we can go back to the question about K-theory. Can this space be described by equivariant algebraic K-theory? And so combined so I told you the story kind of in the opposite way of which it happened in time, right? So first, Carrie and I did this part about equivariant K-theory with the hope that it would fit into such a connection. And more recently, in the last years, we have been, really thinking with Tom and Kiyoshi about this more geometric part and how to define the equivariant H-coordinate space and all these things. Right, so combined with our, but now I'm going to explain it in reverse order. So I will tell you now a little bit about the K-theory story and how you build a K-theory that fits with the story. And that's also an advertisement for Clark's talk, who's going to talk more about spectral Mackey functors. So it will turn out that we really need spectral Mackey functors. So combined with previous work, of Malkiewicz and myself, what we can say is that there is a fiber sequence. Okay, so for the rest of the talk, I'm going to define this guy, equivariant A-theory. So we can just take this to be the co-fiber here. And it's exactly what we wanted. If I take the fixed points and the underlying infinite loop space of this looped space, this is equivalent to the stabilized, with respect to representations, equivariant H-coordinate space. Okay, so I guess this is good, but we still don't know how to actually, right? So it still remains as an open question whether you can actually, whether you can split this map. And I said it as a conjecture. To be honest, I'm not even 100% sure if it's necessarily true anymore. So there's for sure some potential obstructions to compatibility with transfers in the equivariant case. Okay, so now for the rest of the talk, let me explain how you construct this equivariant A-theory spectrum that has these properties. So for sure, right, what we knew we wanted from the very beginning, right? So even though it takes forever, to prove these things about H-cobordism spaces, because there's just so many technical things that you have to deal with, and years of figuring out things for manifolds with corners and so on. But the result, I think, we had talked to Tom Goodwillie about such a result, like he had told us this idea ages ago, and this is what motivated this entire work. And so this is why we knew that, okay, if you can define this with the property that this splits over conjugacy classes into A-theory terms like this, this would have the potential to fit into this story. And I think, John Rognes has also thought about this in the 90s. So I think this was a question of interest, right? Precisely because of a desired such theorem. And what was also known is that, right? So you can construct something with such a splitting if you take K-theory of okay, and this was done by John Rognes. So he sent me some notes. I think these are not public to everyone, but it's also written recently by Badrich and Dorabiala, who were talking to us at the time. So this is now just fixed point level, right? So this now is retractive G spaces over X. Okay, so now here X is a G space. And G maps. And what is the Waldhausen structure? So it's the genuine Waldhausen structure. So in particular, right, G weak equivalences. So equivalences on fixed points, not just coarse ones. Okay, and then also, right, by genuine Waldhausen structure, I mean the cofibrations are also G cofibrations. The finiteness condition is also G cell complexes relative to X. And so what this is not, right, so note that if X is a G space, you get an action of G on the category of retractive spaces over X just by conjugation. And so this is not the same as just the homotopy fixed points of this action. So it is the same, so same objects and morphisms, but different Waldhausen structure. So this one has what I'll call, Mike hates naive, I'll call it coarse. Okay, so this will not be naive anyway. So this is just underlined. It's not even naive. So the coarse Waldhausen structure, where coarse just means you have G maps, you have equivalences, but they're just underlying G maps that are non-equivariant equivalences. The finiteness condition also, everything is just non-equivariant, but they're G maps. Okay, so it turns out that, so this is something that's easier to handle. You can actually, this one, you could explicitly deloop, even if you wanted to explicitly get deloopings at the space level. And so this is something that Kerry and I called AG coarse, and it's an interesting thing. So its fixed points turn out to be this bivariant A-theory of Bruce Williams of a fibration. It's not a not interesting object, but it's not what we wanted for the connection to So in order to, okay, so what makes it possible now, right? So as I said, people were interested in this question, right, throughout time. And what makes it possible now to actually give a G-spectrum with these fixed points is this new machinery of spectral Mackey functors. And you really and absolutely need to use spectral Mackey functors here. So there's no way, so this one you could build even via explicitly looping, but this one, I'm claiming there's no single class of weak equivalences whose fixed points are going to be these correct fixed points for every h, right? So there's no way to start with a single category and a single class of equivalences and take its fixed points and get these things. So you really have to assemble these one at a time. So they declare your fixed points, what you want them to be, and assemble them into a G-spectrum. So now to kind of make the bridge to Clark's talk also and advertise a little, and then Clark will tell you the fancier version of everything. So let me just tell you the less fancy version. So just give you an idea of what is a spectral Mackey functor, and we built Mackey functors of Waldhausen categories, and then Clark will tell you how to even make Mackey functors of infinity Waldhausen. Don't disappoint. So yeah, you can make then Mackey functors of infinity Waldhausen categories, and so you can make Mackey functors in many scenarios, and this has been a very powerful technology. Okay, so just to bridge kind of from Clover's talk, who told us a lot about Mackey functors, to Clark's talk, so a little bit of interlude on spectral Mackey functors. And also, hopefully, it's good advertisement, because I'm claiming that I think you really need this technology to build this kind of spectrum with these properties, desired properties. Okay, so recall, so let me start with some very, as I said, very easy things. This will be very, hopefully, easy story. So recall what is an AB-enriched one-object category. Okay, so simple question. Right, so it's just, so you have your one-object category and it's AB-enriched, so right, all it means is that you have maps like this. So hooray, this is just a ring, right, in algebra. Okay, easy and nice, right? So now, what is an AB-enriched functor from this AB-enriched category R to AB? Well, it picks out your one object. It's going to be some abelian group, and then R will go to a group of endomorphisms of R. So that gives you an adjoint form, exactly the action. So what it is this is exactly the data of a module M over R. Okay, so now, to make this more fun, and this is Stefan's perspective, or Schwede Shipley. Do you not want to?
Wait and see what's coming.
Okay, yes. Yeah, don't commit to it yet, because maybe. Okay, so. Okay, Stefan did not approve yet, but. So Schwede Shipley perspective, I'll call it. Okay, so what is an AB-enriched category? Let's still call it R. Well, what does it mean to be AB-enriched? If these are objects in R, and let's suppose everything is small, right? What it means is you have, sorry, maybe ABC, that you have maps like this. So AB, BC, okay, AC. So we can think of this as a ring on many objects. Right, so it's just like a ring with ring maps, but it has many objects. And these are now our ring maps. And what is an AB, for the bullets here too, what is an AB-enriched functor from such a category are abelian groups, well, again, it will pick out one object M, and every object now of R, A, is going to go to some other abelian group M sub A, and we're also going to get maps, right, we're going to get maps R, A, B, tensor M, A to M, B. So this is what we can think of as a module M over R, where R is a ring on many objects. Okay, nice and simple. So this was all abelian groups. So now, what was Clover's favorite definition of a Mackey functor? So Clover told us her favorite definition in the question session. And I think everybody in the audience agreed who had an opinion, right? So it's also my favorite definition, right? So a Mackey functor is, okay, so this is the Burnside ring. Well, let me just, so what was her favorite definition? It's an ab-enriched functor from the Burnside category to abelian groups, right? So this was the definition, and she maybe stopped short of saying what the Burnside category is, right? So I'm calling this a module over R, where now R is a ring on many object. So it's just a BG module where BG, so the Burnside category, so this is a ring on object set G mod H. And the abelian groups between G mod H and G mod K are defined to be K naught, so the group completion of isoclasses of spans from G mod H to G mod K. Okay, so now you can all guess the definition. What is a spectral Mackey functor? Well, we replace, in everything I said, we just replace ab with spectra. And that's how we get a spectral Mackey functor, as the usual story goes. So a spectral, right, so just replace ab with spectra, and a spectrally enriched functors, right, so we also want to soup up this Burnside category to a ring on many objects in spectra, as opposed to just abelian groups. So a spectral Mackey functor is, well, is a module now in spectra over BG. So now I'm abusing notation. So now BG, so this is now a ring in spectra on object set G mod H. But now I need mapping spectra between G mod H and G mod K. And so instead of applying K naught, I just apply K-theory to the same thing. Well, sorry, to the category, right? So now I need to take the category of spans from G mod H to G mod K. Okay, so let's see. Okay, I have about 6 minutes left. I should probably finish soon. So now all the subtleties start. Okay, so this is the easy thing to say, but now the hard thing starts, right? With like, what kind of K-theory is this? You know, and this was, and then how do you reconcile different kinds of K-theories and make sure that you have the same ring spectrum there and same modules? And this is a lot of hard work. But maybe sweeping this under the rug for now. So let me maybe put this even higher. I think that was all stuff there, right? So the big kind of recent theorem, right, was that BG modules are the same with G spectra, and now many people's names are going to go here, right? So starting with Guillaume, and the heart of their proof is really in a paper also with Angelica and Bert, and also Guillaume, May, Osorno, and then there's other approaches, right? Clark will tell us about this. So Barwick, and then Glassman, Shah, Narvin, and also in an appendix of Naumann, Matthew, and Noel. Maybe I'm missing somebody. There's an appendix written in one of their papers that also treats this theorem. Right, so what it tells us that the usual category that we know, the equivariant stable homotopy, so G spectra is equivalent to BG modules, to spectral Mackey functors. So this is really a very powerful thing, because as I was saying, sometimes you can't build your thing explicitly, and you really want. So I talked a lot about representation last time, right, and suspending with representation. So now this is all hidden, right, in, like, you don't have to even mention representations. You only have non-equivariant spectra, and the work now goes into building these restriction and transfer maps. So whatever you heard in Clover's talk, right, so my time is really running out, so I will maybe just say a few words from here and not write anything down. But right, so you saw Clover in action really manipulating Mackey functors, and it's very similar, except now it should be happening in spectra, but of course it's hard and you can never actually do it in spectra. So usually you want to do some categorical thing and then transport it to spectra. So, and this is where all the bodies are buried, So as I said, right, in this theorem, right, you prove this with some K-theory, and now, so we had to reconcile it we wanted to build Mackey functors of Waldhausen categories, so those categories that I built of, that I mentioned over there, and make modules in Waldhausen categories, right? So this also uses, right, in order to transport a comparison between Siegel and Waldhausen K-theory multiplicatively. So work of Anna Marie and Angelica also goes into that. And Clark will tell you also how to do, as I said, fancier things within Waldhausen infinity Waldhausen categories. But right, you have to go usually back and forth between things and construct your things, and that can be where a lot of the technical work goes. And maybe in the last 2 minutes, so let me just go back, because I remembered I promised you last time I'm going to connect back to the scissors congruence. So let me maybe just say one word. Okay, so that conjecture, right, so now I can explain more what I meant. Right, so in that setting, there should be, right, and we haven't done it yet, there should also be a Mackey functor of squares categories or something like that. And the way to transport it via squares K-theory to spectra. But what we did, right, so recall there was this map from K squares of manifold G boundary N going to, so I said the fixed points of this coefficient system. So these are the fixed points. So this was a gadget defined by Kaje, Chan, and Mejia. And they defined this linearization map. So now I can see, so last time I said there is such a map that records the equivariant Euler characteristic on pi naught. So that was the claim, that in one component, so one of the components is a Burnside ring on pi naught, and this sends some G-manifold to its equivariant Euler characteristic. So now, in the last 40 seconds, I can say, so how this really goes is, it does go through a theory of a point, equivariant A theory of a point, and this is the linearization map, also from, so there's an equivariant linearization map, so same people, and this is how this really goes. So this, of course, is the G fixed point map of a map of genuine G spectra by definition, right? So here there is like more work to do if you wanted to lift it up to a genuine equivariant statement. Okay, so now maybe I should stop here.
questions?
Not we can go to lunch.
I was going to, in the last second, you talked about this map of HE star to KG. How is that automatic output of the machine, or is there work in constructing this map?
Yes, so there is work in constructing this map, and I think it's related to some stuff that you have done. And Andres, have you ever talked to John?
We haven't spoken about it.
All right, so Andres was here, one of the authors, who is my student, will talk to you. So maybe not. So what they have done is they have defined K-theory for coefficient systems. Okay, so let me just say this is much more clever, right? So in my thesis, I was thinking about K-theory just G-rings. And initially, I would have assumed that the target here of a linearization map, or of this, would be Kg of Z. Not linear, but K-theory maybe for the Euler characteristic, but that was too naive, that doesn't work. You really need this coefficient system, and this has a fixed point, so on fixed points it also has a Tom-Dick splitting. In this case, it's just the K-theories of, so it splits into the group ranks of the WHs, but so they have something more general, right, where you can start with any X here. And then they have something more general also that maybe they're thinking about, which is K-theory for green functor. And I think that is related to some of your work. But I should not misinterpret and let Andres actually just talk to you about this.
Thank you.
But yeah, so that's here, you just need a coefficient system, and that's enough to define this for our purposes. But they have something fancier, which is K-theory for green functor.
Questions? If not, we should thank Mona again.